Hi, I'm Dr. Matthew Michael. I'm a lecturer here in the math department at NGRT. Today I'm going to be talking about differential equations, specifically some of the different texts and ideas and concepts from Boyce and DePrima's 10th edition. So these are really supplements to my lectures so you can get an idea of what I'm thinking, so you can get into the mind of a mathematician to try to understand what we're talking about, what we're thinking about, what we're considering when we look at these problems. So we had two sections already, taking a look. What's a characteristic equation? How to solve a characteristic equation? Why do we care about characteristic equations? So if I have this differential equation with constant coefficients, with my characteristic equation here, we get these solutions. Now, in section 3.1, we discussed real and distinct roots, when b squared was bigger than 4ac. Today, we're going to do the opposite. We're going to take a look at when b squared is smaller than 4ac. Because in that case, I'm taking the square root of an imaginary number. So that because of that, I get complex numbers. Because remember that b is out front, right? So that b over 2a, or that negative b over 2a, that's talking about my lambda, some number that's real, plus I, the imaginary number, times another real number, mu. So I'm going to get complex exponentials, which looks a bit bizarre, but here's the really cool part. What makes me so excitable about this lecture in my class is that when we did Taylor series in Calc 2 of the exponential function, and then we plug in an imaginary number in for that, remember we know how I operates, right? So I squared is -1, I cubed is -I, and so on and so forth. So it turns out that these are very predictable power series, very predictable Taylor series. Turns out that the complex exponential is related to cosine and sine. And so since once I plug in mu, I can find out any complex exponential of Euler's formula where e to the I mu t is cosine of mu t plus I sine of mu t. And since addition in exponents means multiplication of the base, I can break it apart. So e to the lambda t plus I mu t becomes e to the lambda t times e to the I mu t. And I know what this is from right above it. So turns out that my complex exponential is an exponential function times a trig function. And in fact, if I plug it into Euler's formula in for both of my solutions from the previous slide, add and subtract them, it turns out that these solutions, e to the lambda t cosine of mu t and e to the lambda t sine of mu t, are themselves fundamental sets of solutions when I take the Wronskian determinant. That's a lot easier to write because now I don't have imaginary numbers, even though it was in the complex root, it had a complex root, that this imaginary number actually meant something. This means that all this time, the square root of a negative number meant something. Because think about it. Every other function doesn't act like cosine and sine. Exponential functions either go from 0 up to infinity or from infinity down to 0. Polynomials either go from -infinity to infinity or one of the infinities to the same infinity, right? Depending on if it's an odd or real number, odd or even number. So only one that stays consistent and oscillates back and forth is cosine and sine, the trig functions. That's because of that square root of a negative number. That's what makes it really cool. So this slide is a little bit messed up, and I tried to change it, but PowerPoint doesn't want me to change this. So instead of a 9.25 there, I want you to imagine a 1. So this is y double prime plus y prime plus y is equal to 0. When I plug this into the characteristic equation, I get that equation. That is correct. I'm going to build off of this. R squared plus R plus 1 is equal to 0. So finding my R value, I turned out to get -1/2, because it's negative b over 2a, plus or minus the square root of the square root of 3 over 2i. So this means lambda, which is my real part, that negative 1/2, and mu, which is my imaginary part, mu is an imaginary, it's multiplied by imaginary. So it's the part of the r that is connected to the imaginary. That's square root of 3 over 2. And now it's mixing these two up together. So this is square root of 3 over 2 cosine, and this is sine of square root of 3 over 2 as well. So if we use the formula that they have below, we can actually see what this looks like. So let's assume that their form is correct, that they're flipping back and forth between their mistakes here. What we have here is a wiggle, right? Cosine and sine are wiggling. My students will probably giggle over the fact that I call it wiggling. But we have cosine and sine oscillating, right? But it's multiplied by a decaying exponential. This is an exponential that is has a negative root, so it's shrinking. So that exponential is describing kind of its amplitude. And because it's shrinking in size, the amplitude of the wiggles, the amplitude of the oscillations are decaying down to 0. Now, should I have a different formula, have a different setup, I could get a positive root for the exponential. In this case, I have something that is growing in size. So this is a case almost of if you put a mic in front of a speaker, you kind of get those surges of sound that cause shrieks and cause everybody to put their hand over their ears. I want to call it reverb, but I know it's not reverb. It's that buildup of sound where it keeps growing and growing and growing and growing, and then poof, something that blows up on you. Notice in this case, I can get purely imaginary numbers, though. So whereas this had a complex root with a real part and an imaginary part, stuff like this, which is similar to, say, our voices, helps describe purely imaginary. So this is a case of cosine and sine. So there's no decay here because there's no exponential. Hope this helps.